Let's just conclude our section on suspension bridges by looking at a real bridge so we can see what elements are captured by our simple model and our simple analysis. So let's look at the suspension bridge, the Golden Gate Bridge in San Francisco. It's quite recognizable, so even if you've never seen it in real life, you probably recognize instantly the picture here. It's quite massive bridge, so the span between these two towers is about 4,000 feet, so almost nearly a mile. And we see the kind of familiar shape of the cables running between these two towers, and then cables which run off to the shore on the left and the right. So we can see the shape of the cable and the structure a little bit better if we look at it from the side. And so this ought to look quite familiar from our last video. And in fact, if we print the image here, and I take my string and weights and I lay it over 2 points which are aligned at the tops of the towers, and I tape it to the shore, I can get a shape of this main cable that looks pretty much exactly like the real thing. So we see that the form by my simple model is quite accurate for what the real structure looks like. Now, of course, the real structure has many vertical cables, which is holding the roadway up, whereas I have a finite number, but you can see the cable is still quite smooth, the main cable across the top. You'll also notice that rather than holding up discrete weights, the real bridge is holding up a truss structure, which is what the roadway sits on. And one function of that is not only to have something for the cars to drive on, but the truss is used to add some stiffness such that any additional weight which comes at any point. So for example, if a bunch of trucks or something piled up and all sat here, in our weight model, if I added a little bit of extra weight on this vertical cable here, it would pull the main cable down. In the real bridge, since the truss of the roadway is stiff, even if we add extra load at this point, the main cable will pretty much preserve its shape. So the shape will be fixed once the bridge is built. So let's look at the shore a little bit more closely. So as we discussed in the last video, if we didn't have this cable going off to the right here, all the weight of this roadway in the middle of the main span would be held up by these towers. So not only would all that weight be pulling down into the ground, but the tension of this main cable would be wanting to pull those towers inwards to collapse into the water. So that wouldn't be a good thing. So we drape the cable over the structure and then we anchor it right here into the bedrock. Now you can tell that this cable is quite tight because it's very, very straight, even though it's holding up quite a significant load for this span of the bridge going from the main tower to the shoreline. And so again, the function of that is to make this tension and this tension balance so that the reaction of the tower is going straight down to the ground. We see something similar but maybe a little bit different on the other side of the roadway. The cable comes in, anchors here, so it actually passes through this truss structure of this extra chunk of the bridge here. Now, in the large view, the cable looks like a string, so it looks very thin. When you're up close to it, it's quite massive, so it's about 3 feet in diameter, and it's made of many, many cables that have kind of a cross-section that you see here. And if you look on YouTube, you can find some fascinating videos showing the construction of the bridge, which are actually quite nice to look at, because then it really gives you a sense of how the bridge is being held up. So here you can see the roadway going out both left and right from one of these main towers, such that these will meet in the middle. And when you look at the thing from the top and you imagine the work that these people did to construct this bridge, it looks quite terrifying. So I certainly wouldn't want to be up here.